In this third session, we're going to do aldehydes and ketones. So the question we were given was draw the reagent, major product, or provide necessary reagents for each of the single-step transformations shown below. You may assume standard conditions to achieve a neutral stable product. So this question is coming from ketones and aldehydes. And for us to answer these questions, we must know the oxidation or reduction of ketones and aldehydes. So this is what we need to understand. So before we can answer this question from CHE 2105, that is chemistry, let's try to first understand what they simply mean when they reduce an aldehyde or a ketone, and also when they oxidize an alcohol. So let's try to understand these two terms before we can even go any further. So this was April tutorial sheet, question 4. Okay, let's understand this. So the first thing we must understand is about oxidation of alcohols. So oxidation of alcohols. So one thing I want us to understand is that when you oxidize a primary alcohol, we are simply going to form an aldehyde. So oxidation of primary alcohols forms aldehydes, then oxidation of secondary alcohols form a ketone. Okay, so this is actually opposite of reduction. When you're doing reduction, for reduction, okay, for reduction, if we reduce aldehydes, we are going to form a primary alcohol. So it's just the opposite. Then if we reduce a ketone, we are going to form a secondary alcohol. So this is the prerequisite knowledge we must have as we are solving these questions. Okay, now let's answer the question. So for the first one, we have this group, this side, which is just a carboxylic acid. Then we have an aldehyde group, this side. So the reagent we've been given, it is sodium borohydride. So if I try to zoom this, so the reagent we've been given is actually this reagent here, which is sodium borohydride. So let's try to see how we can answer this question. Sodium borohydride, one thing we must know about this one is that it is a good reducing agent. Okay, so it is a reducing agent, and because it is a reducing agent, so it is going just to reduce this aldehyde there. Carboxylic acid won't be affected. The carboxylic acid cannot be reduced by this sodium borohydride. So let's see how we are going to write the structure. So we can count the number of carbons. So we have 1, 2, 3, 4, 5, 6. So it is 1, 2, 3, 4, 5, 6. Okay. Then here we have OH. Like that. Then there we have a double bond with oxygen there. So this is the carboxylic group. Then we need now to consider this aldehyde, and from what we just said, we said when we reduce aldehydes, they simply form primary alcohols. That is what we said. So because they are forming primary alcohols, meaning that we must add a primary alcohol to this end point. Okay, so we must add a primary alcohol. So we just need to maintain the number of carbons. So we have 1, 2, 3, 4, 5, 6. Okay, so even here 1, 2, 3, 4, 5, 6. Then we're going to add a primary alcohol like that. So this is the solution for the first question. The aldehyde has been reduced to a primary alcohol. Let's look at the second one. So for the second one, we have a secondary alcohol and also an aldehyde this side, and we are using this compound, which is PCC. So PCC is just a pyridinium chloride. Okay, this is pyridinium chloride. The spelling is actually this. So pyridinium chloride. So that is what they mean by PCC. Then for this one, we said it is sodium borohydride. Okay, so we must know that. Okay, so for this one, it is also it's a reducing agent. Okay, so it's going to reduce this compound. All right, so as we said, this group, since we have PCC, which is the pyridinium chloride, and we have a secondary alcohol rather. For this one, sorry, it is not a reducing agent but an oxidizing agent. So we are simply trying to oxidize the secondary alcohol so that you can form a ketone. And because it is an oxidizing agent, but there's an exception. Okay, one exception is that this one does not oxidize an aldehyde. so it doesn't oxidize aldehydes. Okay, so that is one thing we must understand. So what we are saying is that let's count the number of carbons: 1, 2, 3, 4, 5. Okay, so we are going to have this 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5. Okay, like that. Then at this group, which is an alcohol, this is a secondary alcohol. So for secondary alcohol, when they undergo oxidation, we said they form ketone. So at this same position, you must have a ketone like that. Then we said pyridinium chloride does not oxidize aldehydes. So at that end position, we are simply going to have the same aldehyde like that. Okay, so this is the product for the second one. Now let's look at the third structure. So for the third structure, we can see that we have zinc, mercury, then we have also hydronium ion. So this one is what is known as a chromosome reduction. So for a chromosome reduction, one thing we must understand here is that it is, if you have this zinc, mercury together with the hydronium ion, it is able to reduce the aldehydes and the ketones you have to alkanes. Okay, so that is very important for us to take note. So what I'm saying is that it is able to reduce this one. It is able to reduce aldehydes and ketones to alkanes. So it's able to form alkanes from these aldehydes and ketones. That is what we need to understand there. So let's now write the structure. So the structure will be in this manner. Okay, so we are going to start with the alcohol. So for the alcohol, it won't be reduced because we're saying that this chromosome reduction is just able to reduce the aldehyde and the ketones to alkanes. But since we have an alcohol, meaning that nothing will happen to this alcohol. So we're going to start like that. So we have HO. Then we have this. Then we have a cyclohexane like that. Okay, then we have, okay, so this side we can see that it's a carbonyl bonded to a hydrogen, meaning that this is an aldehyde, and because it's an aldehyde, according to chromosome reduction, we said that it's able to reduce this aldehyde to form an alkane. Okay, so because it is forming an alkane, meaning that this group here is going to be detached, then we are just going to replace with an alkane. So we'll just add an ethyl because it is just one thing which is being removed. So we are able to add a branch like that. That is an alkane. So this is the structure it's going to form. So what we need to take home here is that for chromosome reduction, when you have the zinc zinc mercury in the presence of hydronium ion, it is able to reduce the aldehyde and ketones to alkanes. So that is the take-home message here. Then let's look at part D. Part D, as we can see, we have already the reactant and also the product. The only thing they're asking us here is to show the reagent which was used in order to come up with this product. And we can say that at one point they had to break this double bond here, and there was something which was now attached. So from the look of the things which took place here, we can see that it was just the reaction which is known as the Grignard reagent reaction. So the Grignard reagent was added to this reactant in order to form this long chain here. So the Grignard reagent, we say it is an organometallic, meaning that it is maybe a metallic bonded to a certain halogen, like magnesium, bonded to this bromine, which is just an halogen. So we are saying that it is an halogen MgBr. Now let's see the branches it has to have. Like this double bond was broken, so it was removed. So this Grignard reagent, we say that the MgBr, it leaves, right? Then whatever remains is what is attacked by the double bond, so that there is that connection, the reaction to take place. Okay, so one thing we need to take note is we just need to count the number of the carbons which are added. So from this bond you can see that there are how many carbons. So there are about 2 carbons this which were added. So these 2 carbons, so there are 1 2, actually there are 3. The 3 carbons were added to this after the double bond was broken. So meaning that we just need to attach a propyl to this Grignard reagent. So it was just a propyl like that, or should I say, so if we count, let me just erase this. So it was from here 1 2, but here we have 1 2 3 4. Okay, so they had to add this chain here for them to come up with this prolonged product. So it was just an ethyl. In fact, it was an ethyl, not a propyl. So an ethyl then bonded to the Grignard, bonded to an organometallic, which is magnesium bromide. So this is this had to leave. Then after it left, then this carbocation had to attack. That's that point. Then there was this connection. So this is where we end with question 4 on aldehyde and ketones. Thank you for watching, and don't forget to subscribe and also like and share.
na wewe sana lembe kwa nani sababu ngata akule mbele. Ana tajana ni mbaki. Watu hatumaga.